All right, in this video, I'm going to cover section 3.1, interpolation and the Lagrange polynomial. So let me briefly what interpolation Lagrange polynomial and the interpolation Lagrange polynomial means. Okay, so interpolation is the process uh, to estimate or approximate data using a function. Okay, so then just let's jump into the Lagrange polynomial. Okay, you need to. Um, I'm gonna the visualize what Lagrange polynomial the is. Okay, so the first one, we're gonna let's just define function L0. Okay, so x is x minus x1 over x0 x naught minus x1. Okay, and then L1 of x, okay, is x minus x naught over x1 minus x naught. Okay, so okay, out of blue, what's the x naught and x1? So think about this. Here is the x-axis, okay, and then let's say this is y-axis. All right, and so let's say we have a whole bunch of data, okay, in the two dimensions space. Okay, so y-axis right here. So maybe hit the point right there, and then point right there, and then maybe point right here. Okay, something like this. Okay, so I mean, let's say this is the coordinate. The first point is just x naught, and then you know y naught. Okay, so this is x1, and and then this is y1. Okay, so this is x2, x3. Okay, this is a given point. Okay, so this is a given point. We want to approximate the function which pass through all the points given. Okay, all the data itself. Okay, these points can be considered as data. Okay, so here is y3, then there's y4. Okay, so anyway, we just focus on 2 points. Okay, so x naught and x1. Okay, so now then we can define L naught and L1 like this. All right, then give me a second. So then what does these two functions look like? Actually, this is a linear function, right? That's also a linear function. They are linear functions. Let me plot the graph of L naught L1 in the other xy plane. Okay, so the x-axis here is x naught, here's x1. Okay, so now then what? The if x is, think about this. If L in the function L naught of x, if x is equal to x naught, what? Then L naught of x not gonna be 1, right? Okay, so here's a 1 right here. Okay, what if x equals x1? Then x1 minus x1 is 0. So this function, the value of this function must be 0 at x is equal to x1. So we're gonna get this graph. Okay. I mean, just think about in the graph of this one from x naught to x1. Okay, and that integral. Okay. Then what about L1? L1x, if x is equal to x naught, then x naught minus x naught is 0, right? So it's 0. What if x equals x, well, we plug in x1 into x, L function L1, then we're gonna get 1, right? So we get this function. You see, it makes sense, right? So now this is the L naught of x. Okay, this is the L1 of x, right? So what are you going to do? So using those two functions are examples of Lagrange polynomial degree 1. Okay, first degree Lagrange um, interpolating polynomial. I'm sorry, interpolating polynomial. This is an example of the Lagrange first degree. Okay. First degree. Sorry. Lagrange interpolating polynomial. Okay. So now using this one, we're gonna construct the Lagrange polynomial. So what does that mean? Lagrange polynomial. Lagrange polynomial, the function, polynomial function. Okay, polynomial function that fit the given data. Okay, and then we construct Lagrange polynomial using the Lagrange interpolating polynomial. Okay, so now we're gonna construct the p of x as like this, L naught of x. Okay, and then now let me rewrite these y coordinates of given data as function notation. Okay, so this is the f of x naught. Okay, so this is the f of x3, and then this is f of x1. It makes sense, right? I know. So, I mean, in reality, in practice, normally we don't know function f. Okay, we, I mean, what we are given is just only data. Okay, but just let's say just um, yeah, we know the function. Okay, I mean, of the function that pass through all the data exactly. But so okay, so this is L naught x and then f of x naught plus L1 of x times f of x1. Okay, then what happened? So look at this. F of x naught is a real number, right? Okay. Even I don't know, maybe probably even if f is a non-polynomial function, the evaluation f at x naught going to be what? The output must be a real number. So this is a real number. L naught of x is what? Polynomial, actual linear function, right? This is a polynomial. That's a real number. So sum of two polynomial is what? Polynomial. So p of x is polynomial, right? Okay. And then p of x naught is equal to p of x naught is what? L0 and then x, L naught of x naught and then f of x naught plus L1 of x naught and then times f of x1, right? So, but you know what? L1 of x naught is what? You see that L1 of x naught is what? 0. So this is going to be 0. So the L naught of x naught is what? 1. So this is 1. So we're going to get what? We're going to get f of x naught, right? Similarly, p of x1 must be equal to what? P of x1 must be equal to f of x1. So this function is a polynomial function, and then the pass through the two given points, x naught comma f of x naught and the x1 comma f of x1. Okay. How did this function pass through those 2 points exactly? Because of that Lagrange interpolating polynomial. So as long as we know the finite number of points, then we can construct the Lagrange interpolating polynomial, and then using Lagrange interpolating polynomial, we can construct the Lagrange polynomial, which is this. P of x is equal to Lagrange polynomial, which is polynomial functions and pass through the data. Okay, so finally, we construct the Lagrange polynomial only 2 points. These are called the nodes. We'll see that. Okay, nodes. So but so nodes, but the depending on nodes, the degree of Lagrange interpolynomial will be determined. But so we can construct the Lagrange interpolynomial using four nodes, 4 points, or we can say 4 nodes, and then we construct the Lagrange polynomial. Then maybe we can get this kind of the functions. Okay, so Lagrange polynomial functions, and then so the and then let's see the my lecture note. Okay, and then I'll just continue to explain about the Lagrange polynomial. Okay. All right, so here I told you interpolation is a process of prediction or estimation of a data using a function that fits the given data. Okay, so first one, so then how can you guarantee that the Lagrange polynomial, um, the approximate uh, a function, of the given data? So we can guarantee that that polynomial Lagrange polynomial can be used as approximate function of the function of given data based on that while that theorem. It's because it's all stress approximation theorems. Okay, so the where stress approximate theorem says that suppose the f is defined and continues on closed interval a comma b, then for each epsilon is a positive real number, there exists p of x polynomial function such that, you see that this is absolute value error, right? Absolute value error is less than epsilon for any x. Okay, so for each epsilon, so what if we just we set 10 to the negative 8th power? Okay, 10 to the negative 8th power. This is really I mean small number. I mean all is close to 0, right? So for each epsilon, and then we set the 10 to negative 8, even though we set the 10 epsilon 10 to negative 8th power, so which is really close to 0, there exists p of x. That theorem guarantees that existence of that polynomial function, so that the absolute value error f of x minus p of x is less than epsilon. So now you see, because of that theorem, we can guarantee that Lagrange polynomial, what the can be considered as what the approximate solution, approximate function of the f of x. Okay, so now the I told let's see that section 3.1. So I just show you, I did show you what L of L naught and L1 looks like, right? And then I construct the P of x, and I show you P of x naught and P of x naught return the f of x naught, and the P of x1 return the f of x1, right? So P of x is a unique linear function passing through, yeah, x naught comma y. This two data, x naught comma y naught, and the x1 comma y1. Okay. So now then, we're going to generalize that Lagrange polynomial. Okay. First one, we're going to construct the Lagrange interpolating polynomial, nth degree. You see that nth degree Lagrange interpolating polynomial. Okay. So then we're going to consider n plus 1 point. Why we consider n plus 1, not n, but n plus 1? Because you see that to construct a linear degree 1 Lagrange interpolynomial, we needed two data, right? X0 and x1. So to construct the nth degree Lagrange polynomial, we need n plus 1 point. Okay, keep in mind this. It's quite yeah, quite basic, but it's important. Okay, so now let me introduce the notation of Lagrange polynomial L sub n comma k of xi. Definitely xi represent what nodes. What's the nodes? X naught through xn are called the nodes. Okay, n nodes. So x coordinate of data is called nodes. Okay. So now then n is the degree, represent degree. K represent index of Lagrange polynomial. What does that mean? Back to the linear polynomial. You see that L naught L1 for one degree 1 Lagrange polynomial. We got two. We got two Lagrange polynomial, right? Makes sense. So that sub-index, not L, 0 and 1 represent index of Lagrange polynomial. To construct the degree 1 Lagrange polynomial, we need two data, and then we're gonna get two Lagrange polynomials. And then for nth degree Lagrange polynomial, to construct that, we need n plus 1 nodes, and then we're gonna get what the we're gonna get the n plus 1 Lagrange polynomials. Okay, so keep in mind this. So now, so definitely k goes from 0 to the n, right? K goes 0 to n. I goes 0 to n. Okay, so if k is equal to I, k is equal to I, that Lagrange polynomial return 1. If k is not equal to I, that Lagrange polynomial returns 0. How come? We already figured out the pattern here. You see that in the graph of L0 and L1. Give me a second. So in this figure, you know, we figured out the L0 of what, x0 is equal to 1, right? And the L0 of x1 is equal to 1, and this is 0, right? And then L1 of x0 is 0, and the L1 of x1 equals 1. You see that? If the that's the represent index, okay? So following the index what we show in the lecture note, then this can be written as L1 comma 0 and L1 comma 0, L1 comma 1, L1 comma 1. Okay. So now they see that k equals 0 and then I is 0. If k is equal to I, then return 1. And then k equals 0 and then k is 1. I is equals 1. I is 1, right? So k is not equal to I, then 0. You see that? The pattern, right? So now the so we see the why the this along the polynomial returns 0 and 1. So yeah, so we need to definitely we need to construct the Lagrange polynomial that has that property. Okay. The way is to construct the Lagrange polynomial having that property is this: x minus x naught times through the x minus xn over xk minus x0 through the xk minus xn. So here, you see the bottom, the new denominator is what? The number, okay? There is no x involved. X is an x, a variable x is not involved, okay? So the top one is exactly, you see the compare the numerator denominators. Numerators, the form of numerators is really similar to the form of denominator, right? But except for what? The x, except for xk, I mean. Okay, instead of xk, we put the x right here. And then the interesting is this: x minus xk is not seen in here. That makes sense, right? If you see that there is xk minus xk in the bottom, we're gonna get 0 in the denominator. It's not defined in mathematics, right? So we're gonna get big trouble. So that's the nth Lagrange interpolating polynomial. So we're gonna use this one to construct the Lagrange polynomial. Okay, so now it's theorem 3.2. If x0 through the xn are n plus 1 distinct numbers and f is a function. So these are nodes, and then f is a function maybe whose values are given at these numbers. Yeah, so I know. So I told you in reality, we don't know f. Okay, we only given the data x nodes and corresponding y coordinate, but say the y coordinate of these nodes can be expressed as f, okay, f of xk like this, okay. So then a unique polynomial f p of x of degree at most n exists with f of xk is equal to p of xk. So we wanna then this theorem guarantee that what the uniqueness and the eigenousness of the polynomial function, get that fit the what the points n plus 1 points, okay. So then what's this? We already saw that, right? We already saw that. So how to construct the Lagrange polynomial, right? P of x is defined by f of x naught times ln comma 0 of x. This is what? Nth degree Lagrange polynomial. I mean, the first, um, I mean, first Lagrange interpolating polynomial, degree n, okay? So then this function must be it must be equal to 1 at x is equal to x naught. And then that Lagrange polynomial, you see that here? I'm talking about this one, L sub n comma 0, okay? That Lagrange interpolating polynomial must be 0 at all other nodes, x1 through xn, okay? So now, then we can express we can shorten that expression using sigma notation, okay? And then also we can shorten the expression of the Lagrange interpolating polynomial like this. Okay, but keep in mind this, that's just mathematical expressions. When you implement the algorithm, yeah, this is going to be a whole different story. Okay, first one, if you use a MATLAB or Octave, the the index of the array must start from 1, right? Not 0. That's a big problem, right? So don't be confused. But in next video, I'm going to the explain how to write the how to implement the algorithm into MATLAB. Okay, so you can that will help you to the implement that algorithm of the like interpolating polynomials. So, but let me give one more example. The let's see. Uh, so example one, this is in textbook. So using the numbers or nodes, x naught, x1, x2 is a 2, 2.5, 4. Okay, to find the second interpolating polynomial. So let me second degree. Okay, so for f of x is equal to 1 over x, required that we determine the coefficient polynomial L naught, L1, L2 in um, in nested form. They are this, but okay, so it's not a big deal to figure out interpolating polynomial. Just apply the formula what we was seen in the previous the page into this problem. Okay, but what does this interpolating polynomial look like? Let's figure out that. All right, so we're talking about the approximate the polynomial pass through the 3 points, right? 2, 2.5, and 4. This is x naught, this is x1, this is x2, right? Okay, so then so the 3 points. Okay, 3 points right there. Okay, so it's gonna be x naught comma f of x naught, right? And then x1 comma f of x1, and then x2 comma f of x2. But I told you normally the just 3 points are given. The definition of function normally are not given, okay? Because we assume that we don't know function f of x, okay? So only the 3 points are given. So now then, what are you gonna do? So we construct L naught, right? So since 3 points are given, what does that mean? From here, we can figure out the what? N plus 1. I mean, this is n plus 1. It means that n equals 2. So we can construct the degree 2 Lagrange polynomial, right? Interpolating polynomial. So now L2, comma 0 of x, L2, comma 1 of x. And there also how many Lagrange interpolating polynomial we can construct? 3, n plus 1, okay? Number of Lagrange interpolating we can construct must be equal to what? Number of nodes. How many nodes here? 3, okay? It means n equals 2, so degree is 2, okay? How many Lagrange interpolating polynomial we can construct? Construct 3. So L2, comma 2 of x equals right here. So now the x minus, you see that the 0 right there? Then the bottom one was what? X naught minus x0, x1, right? And the x naught minus x2. Top one is x minus x1, and then x minus x2. Okay, all right. So now this is and then yeah. So the result should be in my lecture note. Look at that, okay? But I want to focus on what does these Lagrange interpolating polynomials look like. Okay, so I will just want to figure out the graph of these 3 functions. So now the L2, so see, a second right here. So this x-axis, so it's x naught, x1, and here's x4, right? So it's graph. So now first one, the L2 comma 0 x must be what 1 at x naught. Here's 1, okay? And then L2 comma 0 of x must be 0 at x1 and x2, okay? Okay. And then what? This guy is what? Degree 2 polynomial. It means these are what? Quadratic functions. Quadratic function, the graph of quadratic function must be what? Parabola, right? Parabola opens up and down, right? So then what? The graph must be like this. You see that? Okay. This is L0, L2 comma 0. Okay. And then what about the L2 comma 1x? This function must be 1, okay, at x equals x1 and 0 at other nodes. Okay. So right here, the graph must be like this. Okay. That must be L2 comma 1. Okay. And the L2 comma 2 must be what? Like this. Okay. And it's a little bit, it should be more curved. Okay. Please understand that. Okay. So this is the L2 comma 2. Okay. Why do am I just, why do I just plot the graph of this one? That will, when you write the code and then if you got error or first thing you have to do is to plot the graph of Lagrange interpolating polynomial to see the graphs look like this, or degree 2, and yeah, for in the case of the n equals 2. Okay, so using three Lagrange interpolating polynomial combination of three Lagrange interpolating polynomial, we construct the p of x. Okay, so p of x, in this case p of x is going to be what? The L2 comma 0x times f of x naught plus L2 comma 1 of x, f of x1 plus L2 comma 2 of x, and then f of x2. Okay, in short expression is my sigma, right? And then I goes 0 through the n, in this case 2, right? And the L2 comma I of x times f of xi, right? Okay, so now then, since this is a what? Quadratic polynomial, quadratic polynomial, quadratic polynomial. So all three terms are quadratic polynomial function, right? So some of the quadratic polynomial is what? Quadratic polynomial function. So this is quadratic polynomial. So now graph of P of x, okay, approximately graph P of x must be like this. Definitely this guy, P of x, must pass through the design. This one, P of x was designed to pass through the three data point, okay? So graph must be, I'm sure the graph must be like this. Like this. I'm sure that. Okay. So now, see, so that's the can be used to approximate polynomial, like a Taylor polynomial extension. See, we could use the in calculus too. We learned that the Taylor polynomial Taylor's polynomial. We use Taylor polynomial to approximate the non-polynomial functions. Likewise, we could use this one to approximate the other functions. But not only functions, also we can use this one to approximate, to figure out the function passing through the given data. Okay, so and then this is better than Taylor polynomial, because Taylor polynomial is just what the use only one data point, but this one use a multiple data point, right? All right, so in this example, so the yeah, we figured out the we compared the f of x and p of x. So we are talking about the example 1 textbook, okay? So the see that f of 3 is a 1/3, that makes sense, and then p of 3 is turns out that p of 3 is a 0.325. So pretty similar, right? 1/3. But if you want to increase the accuracy of the Lagrange polynomial, just we need more nodes, okay? Then the accuracy will be decreased, okay, reduced, okay? So let me stop here, and the next video I'm going to cover how to implement the algorithm Okay, and then I'm going to explain the error. Okay, so let me stop here.